Close your eyes for a moment and listen not to the sounds around you, but to the whispers of the universe itself. There's a faint, almost imperceptible hum, an echo from the dawn of time, ringing through the cosmos like a ghostly radio signal. This isn't science fiction, it's real. It's the cosmic microwave background, the afterglow of the Big Bang, a relic from 13.8 billion years ago that still surrounds us today. Picture it like the universe's oldest photograph, a snapshot taken when everything, galaxies, stars, even atoms, was just a spark in the darkness. But here's the thing, this ancient light isn't just a remnant of the past. It's a treasure chest of unsolved mysteries, 25 of them, each one a cosmic riddle that could shatter our understanding of reality as we know it. Imagine holding a piece of the universe's birth certificate, one so fragile and intricate that it reveals secrets we're only beginning to decode. The cosmic microwave background isn't just noise, it's a fingerprint, a unique pattern etched into the fabric of space itself. Every slight fluctuation in its temperature, every ripple in its glow tells a story. Some of those stories line up neatly with our theories, others. They defy explanation, leaving scientists scratching their heads. What if this faint echo holds clues to missing dimensions, parallel universes, or even the true nature of dark matter? The possibilities are as vast as the cosmos itself. This isn't just about distant stars or abstract physics, it's about us. Every time we peer into that cosmic afterglow, we're unraveling our own origins, piecing together how everything we know came to exist. It's like finding a time capsule buried by the universe, one that challenges us to ask bigger questions, to dream bigger dreams. And that's what makes these 25 mysteries so electrifying. They're not just puzzles for astronomers, they're invitations for all of us to stare into the void and wonder. So let's begin this journey together, tracing the echoes of creation itself and uncovering the secrets hidden in the oldest light there is. One of the most baffling clues hidden in the cosmic microwave background is something called the horizon problem. Picture this: the afterglow of the Big Bang shows nearly identical temperatures in all directions, no matter where we look. That might sound like a minor detail, but here's the catch. Those regions of space were so far apart when the universe was young that light, traveling at its maximum speed, shouldn't have had enough time to reach from one side to the other. In other words, these areas were causally disconnected, like two people whispering the exact same word on opposite sides of a football stadium without ever speaking to each other. Yet somehow they're in perfect sync. Classical physics says that shouldn't be possible. To solve this cosmic riddle, scientists proposed a radical idea: cosmic inflation. Think of the early universe not as expanding smoothly, but as ballooning outward at an unimaginable speed, stretching space itself faster than light could travel. In a fraction of a second, the entire cosmos went from smaller than an atom to something vast enough to explain the uniformity we see today. Inflation smooths out the wrinkles, ironing the universe into the eerily consistent temperature map we observe. It's an elegant fix, but here's the twist: inflation itself is still just a theory. We don't know what caused it, why it stopped, or if it even happened at all. Some researchers argue for wild alternatives, like the speed of light being much faster in the early universe, allowing distant regions to exchange heat before settling into equilibrium. Others suggest even more exotic possibilities, like parallel universes bumping into ours and leaving imprints in the CMB. This isn't just some abstract debate, it strikes at the heart of how we understand reality. If inflation is correct, it reshapes our entire cosmic origin story. If not, we might need to rewrite physics itself. The cosmic microwave background isn't just a relic, it's a detective story, and the horizon problem is the first clue that something much stranger lies beneath the surface of our universe. Now imagine staring at a map of the entire universe and spotting a single eerie anomaly, a patch of sky so cold it defies explanation. This is the cold spot, a region in the cosmic microwave background that's chillingly out of place. Stretching an almost incomprehensible 1.8 billion light-years across, it's like a cosmic bruise, a place where the afterglow of the Big Bang is just a whisper colder than the rest. At first glance, you might think it's just a statistical fluke, a random blip in the data, but the odds of that, less than 1 in 50. This isn't just a curiosity, it's a full-blown cosmic mystery. One leading theory points to a supervoid, an enormous, nearly empty region of space where galaxies are scarce and matter is spread thin. In such a void, light traveling through it would lose energy, stretching into longer, colder wavelengths, a phenomenon known as the integrated Sachs-Wolf effect. It's like walking through a wind tunnel. The farther you go, the more drained you feel. But here's the catch. Even the largest known supervoids don't come close to explaining the cold spot's staggering size and temperature drop. It's as if the universe handed us a puzzle piece that doesn't fit any of the boards we've laid out. Then there's the far wilder idea that the cold spot could be evidence of a collision with another universe. According to some interpretations of string theory and multiverse cosmology, our universe might be one bubble in an endless cosmic foam, brushing up against others. If a neighboring universe bumped into ours in the distant past, the energy of that collision could have left a scar, a cold imprint in the CMB. It's a breathtaking thought, but here's the problem. We have no direct way to test this. No telescope can peer beyond the edges of our universe. No experiment can confirm a multiverse yet. What makes the cold spot so tantalizing is that it refuses to fit neatly into any single explanation. It's too big for a supervoid, too precise for random chance, and too strange to ignore. Some researchers have even proposed that it could be a glitch in our measurements, a quirk of how we're interpreting the data. But after years of scrutiny, the cold spot remains a cosmic question mark etched into the oldest light we can see. Whether it's a flaw in our theories, a window into the multiverse, or something entirely unexpected, one thing is clear. The universe is still keeping secrets, and this chilling anomaly might be the key to uncovering them. If the cosmic microwave background were a perfectly shuffled deck of cosmic cards, we'd expect its temperature fluctuations to scatter randomly, no patterns, no hidden order. But what if I told you the universe might be dealing from the bottom of the deck? Enter the so-called axis of evil, one of the most unsettling quirks in the CMB. When scientists mapped the tiny temperature variations across the sky, they noticed something that shouldn't be there. A strange alignment of hot and cold spots, all roughly lining up along a single, invisible axis. It's as if someone drew a faint, ghostly line through the cosmos, and the entire universe tipped its hat to it. This isn't just a minor oddity. It directly challenges the cosmological principle, the bedrock idea that the universe should look the same in all directions on large scales. No preferred direction, no special axis, just uniform, democratic chaos. Yet the axis of evil suggests there might be a cosmic north, a hidden structure imprinted on reality itself. Some researchers argue it's a statistical hiccup, a trick of the data, but the odds of this alignment happening by chance, less than 1 in 1,000. That's like rolling a die 100 times and getting the same number 90 of them. Unlikely doesn't begin to cover it. The wilder theories, this axis could be a fossil from a time before the Big Bang, a scar left by some unimaginable process that shaped the infant universe. Picture a spinning top wobbling as it slows. Some models suggest the early cosmos might have had a preferred rotation, a twist in spacetime that left its mark on the CMB. Others propose even more radical ideas, that our universe is a bubble brushing against another in a vast multiverse, their collision warping space like a fingerprint pressed against glass. But here's the kicker, we can't yet rule out the mundane, subtle errors in how we process CMB data, or even the influence of our own Milky Way's dust could be painting a false signal. Yet every time astronomers tweak their methods, the axis lingers, stubborn as a shadow at noon. Whether it's a flaw in our models, a whisper from beyond the Big Bang, or something else entirely, one thing's certain: the universe isn't playing by the rules we thought we knew. And that's what makes this axis so devilishly intriguing. It's not just a mystery, it's a dare. The universe loves a good surprise, and here's a big one: the cosmic microwave background is too smooth for its own good. According to quantum mechanics, the infant universe should have been a bubbling cauldron of wild energy fluctuations, leaving behind a CMB packed with dramatic, large-scale variations, like a canvas splattered with bold strokes of hot and cold. But when we look at the real data, it's more like a faint watercolor, eerily muted on the grandest scales. This isn't just a minor discrepancy, it's a glaring cosmic contradiction called the missing large-scale anisotropies, and it's throwing a wrench into our most trusted models of the cosmos. At the heart of the puzzle lies the lambda cold dark matter model, or lambdactum, the gold standard for understanding the universe's evolution. It predicts a specific pattern of fluctuations in the CMB based on quantum ripples from the Big Bang amplified by inflation. But when we compare those predictions to actual observations, there's a strange power deficit, a lack of the expected large-scale variations. It's as if someone took the universe's volume knob and turned it down on the biggest cosmic frequencies. Simulations show a sky buzzing with strong, continent-sized waves of temperature variation, while the real CMB whispers where it should shout. So what's silencing the cosmos? One possibility is that inflation didn't play out the way we think. Maybe it lasted just a hair too long, stretching quantum fluctuations so thin that the largest waves were smoothed into near nothingness. Or perhaps there's a fundamental flaw in how we're interpreting gravity on cosmic scales, some twist in general relativity we haven't yet uncovered. A few theorists even float the idea of cosmic topology, where the shape of the universe itself, like a hall of mirrors, could be disguising the true scale of these fluctuations. But here's the twist: the power deficit might not be a flaw at all. It could be a clue. If the anomalies hold up under even sharper scrutiny, they might point toward new physics, something beyond lambdactum tidy equations. Imagine uncovering a law of nature that rewrites how gravity, inflation, or even quantum fields behave across the cosmos. That's the thrill of this mystery. It's not just about fixing a gap in the data. It's about the possibility that the universe is nudging us toward a deeper truth, one hidden in the quietest echoes of the Big Bang. There's something unsettling about the way the universe refuses to behave randomly, especially when we zoom in on the cosmic microwave background's largest patterns. Take the quadrupole and octupole, two of the lowest order multipoles in the CMB. These aren't just abstract mathematical terms, they're like the universe's heartbeat, the slowest, most fundamental rhythms in the afterglow of the Big Bang. And here's the strange part: they're aligned, not perfectly but enough to raise eyebrows. It's as if the cosmos spun a roulette wheel a million times and the ball kept landing on the same few numbers over and over. At first glance, this alignment might seem like a trivial quirk, but think of it like a fingerprint. The unique swirls should be chaotic, yet these particular ridges line up in a way that defies pure chance. The quadrupole, which divides the sky into 4 warm and cool regions, and the octupole, which splits it into 8, show a peculiar preference for the same plane in space. It's as if the early universe had a favorite direction, a cosmic tilt that persisted through billions of years of expansion. The odds of this happening randomly? Less than 1 in 100, so what's behind this eerie synchronicity? One possibility is that the infant universe wasn't just expanding, it was spinning. Picture a newborn star twirling as it collapses under its own gravity. Some theories suggest the entire cosmos might have had a similar rotation, a primordial whirl that left its mark on the CMB. If true, this would upend our assumptions about the Big Bang's perfect symmetry. But here's the problem. A universe-wide spin would require mind-bending physics, like a gravitational tug from dimensions beyond our own. Then there's the skeptical take. Maybe we're seeing an illusion. Our view of the CMB isn't pristine. It's filtered through the Milky Way's dust and gas, which could subtly warp the data. Imagine trying to read a book through frosted glass. The text might seem distorted in ways that aren't really there. Some researchers argue that once we account for these local effects, the alignment might vanish. But after years of recalibrating instruments and refining models, the signal stubbornly lingers. The wildest explanation: this alignment could be a shadow from beyond our observable universe. If the cosmos is vastly larger than what we can see, its true structure might imprint faint directional hints on the CMB, like a distant mountain casting a faint shadow at dawn. It's a tantalizing thought, but also a frustrating one, because if true, we might never have the tools to peer beyond that horizon and confirm it. What makes this mystery so gripping is its sheer audacity. The universe isn't supposed to have a preferred axis, a cosmic north. Yet the evidence keeps pulling us back to the same unnerving conclusion. Either we're missing a fundamental piece of physics, or there's something vast and unseen shaping the fabric of reality itself. And until we crack this code, the quadrupole and octupole alignment remains one of the cosmos' most beguiling riddles. Take a deep breath and look at a map of the cosmic microwave background. Really look at it. At first glance, it might seem like a random scattering of hot and cold flecks, like static on an old television screen. But tilt your head slightly and you might notice something peculiar. The northern half of the sky seems subtly warmer than the southern half. Not by much, just a fraction of a degree, but enough that this so-called hemispherical asymmetry has scientists questioning whether the Big Bang was truly uniform. It's as if the universe was painted with two different brushes, one slightly warmer than the other. This isn't a minor quirk. The standard model of cosmology assumes the universe started with near-perfect symmetry, a homogeneous explosion where matter and energy spread evenly in all directions. Yet the CMB's temperature map tells a different story, one where the cosmos might have been born lopsided. Imagine blowing up a balloon, but one side stretches just a little thinner, creating a faint imbalance that persists even as it inflates. That's the kind of primordial unevenness we might be seeing here. So what could have caused this cosmic tilt? One leading theory points to primordial magnetic fields, vast, ancient webs of magnetism threading through space since the universe's first moments. These fields could have subtly influenced how matter clumped together in those early seconds, leaving one hemisphere slightly denser and warmer than the other. Think of it like stirring cream into coffee. If you don't mix it perfectly, you'll get swirls of uneven temperature. But there's a wilder possibility: the Big Bang wasn't uniform at all. Some models suggest the infant universe might have had regions of higher or lower energy density, like a loaf of bread baked with uneven heat. If true, this would mean our entire cosmic origin story needs rewriting. Instead of a smooth, symmetrical explosion, the birth of everything might have been messier, more chaotic, more human. Of course, skeptics argue this asymmetry could just be a mirage. Dust in our own Milky Way, or even the way we process CMB data, might be casting a faint shadow on the measurements. But here's the thing: the asymmetry persists even after accounting for these local effects. It's not just in one frequency band or one telescope's observations. It's there, stubbornly staring back at us from multiple independent datasets. The implications are staggering. If the universe really did start with a fundamental imbalance, it could explain other lingering mysteries, like why galaxies seem to flow in unexpected directions, or why dark matter isn't distributed quite as evenly as predicted. This isn't just about temperature differences, it's about peering into the very first moments of existence and realizing they might not have been as pristine as we once thought. What makes this asymmetry so haunting is its simplicity. No exotic dimensions, no parallel universes, just a faint, inexplicable tilt in the fabric of reality. And that's the beauty of the cosmic microwave background. It doesn't just answer questions, it asks them quietly but insistently, in the oldest language there is, light. Dark matter is supposed to be the universe's silent puppeteer, invisible, untouchable, yet dictating the motion of galaxies with its gravitational pull. For decades, physicists have been chasing its shadow, convinced it's made of hypothetical particles called WIMP, weakly interacting massive particles. These elusive specks of matter barely interact with normal atoms, but their collective gravity should leave unmistakable fingerprints in the cosmic microwave background. Here's the problem: the CMB's portrait of dark matter doesn't quite match the story told by spinning galaxies. It's as if we're reading two different chapters of the same book, and the plots don't line up. Start with the CMB's take. When scientists analyze its subtle temperature fluctuations, they can reconstruct how dark matter was distributed in the early universe, a cosmic scaffolding that guided the growth of galaxies. The math suggests dark matter should be cold, slow-moving, and clumpy, exactly what WIMP were designed to explain. But zoom in closer to the way galaxies actually rotate and things get messy. Stars on the outer edges of spiral galaxies whirl faster than they should, as if gripped by unseen matter. Yet when we compare these observations to the CMB's predictions, the numbers wobble. Some galaxies seem to have too much dark matter, others too little. It's like baking a cake using a precise recipe, only to find half the slices are inexplicably denser than the rest. The tension doesn't stop there. Underground labs around the world have spent years hunting for WIMP, shielded from cosmic noise in caverns deep beneath mountains. If these particles exist, they should occasionally bump into atomic nuclei, leaving behind faint but detectable signals. After countless experiments with vats of liquid xenon and crystals chilled to near absolute zero. Radio silence, not a single confirmed WIMP collision. Meanwhile, the CMB keeps insisting dark matter is out there, sculpting the universe on grand scales, just not in the way particle physicists expected. So where does that leave us? One possibility is that dark matter isn't one thing but many, a mix of different particles, some heavy like WIMP, others lighter and stranger. Imagine trying to solve a murder mystery where the culprit leaves behind not one set of fingerprints but several, each pointing to a different suspect. Another radical idea: maybe dark matter interacts with itself through some unknown force, creating complex structures that the CMB's broad brush approach can't capture. Picture a swarm of fireflies blinking in sync. From a distance they look like a uniform glow, but up close their intricate patterns emerge, the most tantalizing and unsettling scenario. We might need to rethink gravity itself. Modified Newtonian dynamics, or MUND, suggests that our understanding of gravity is incomplete at galactic scales, eliminating the need for dark matter altogether. But here's the catch: MUND struggles to explain the CMB's flawless dark matter maps. It's like trying to mend a torn tapestry with a single thread. The patch might hold in one spot, but the rest unravels. What makes this mystery so gripping is its sheer audacity. The CMB and galactic rotations are both staring at the same invisible elephant in the room, but they're describing it in ways that refuse to reconcile. Whether it's a flaw in our models, a gap in our experiments, or a signpost to entirely new physics, one thing's clear: the universe's hidden hand is still slipping through our fingers. And every failed detection, every mismatched measurement isn't a dead end, it's a clue, pushing us closer to rewriting the rules of the cosmos. When the universe was just minutes old, it was a nuclear forge, fusing the first atomic nuclei in a process called Big Bang nucleosynthesis. The cosmic microwave background gives us a pristine snapshot of this era, predicting exactly how much hydrogen, helium, and lithium should have been cooked up in those fiery first moments. Hydrogen and helium, spot on, But lithium, the universe seems to have misplaced nearly 3/4 of it. Ancient stars' time capsules from the cosmos' infancy show only a fraction of the lithium the SIMB insists should be there. It's like following a recipe to the letter, only to open the oven and find half the ingredients vanished. This isn't just a minor accounting error. Lithium-7, the isotope produced in abundance during nucleosynthesis, is staggeringly scarce in the oldest stellar populations. Astronomers call this the lithium problem, and it's a gnawing hole in our understanding of both nuclear physics and cosmic evolution. One camp argues the solution lies in stellar processes, that these ancient stars somehow destroyed their lithium over billions of years, perhaps by dredging it down into their cores where nuclear reactions burned it away. Imagine a chef tossing out perfectly good salt because the kitchen was too hot. But models of stellar interiors struggle to explain such extreme depletion without leaving other chemical traces we don't observe. Then there's the far more provocative possibility: our nuclear physics might be incomplete. The rates of key reactions during nucleosynthesis, like the fusion of helium-4 with tritium to form lithium-7, could be miscalculated. Laboratory measurements of these processes are fiendishly difficult, with uncertainties large enough to maybe explain the discrepancy. But tweaking these numbers risks unraveling other carefully balanced predictions, like the CMB's flawless match for helium and deuterium. It's a high-stakes game of Jenga: pull one block and the whole tower wobbles. Or perhaps the answer lies beyond standard cosmology. Some theorists propose exotic early universe physics, like decaying dark matter particles injecting energy into the primordial soup, selectively destroying lithium before stars could form. Picture a cosmic thief sneaking into the kitchen and swiping the lithium before anyone could notice. Others suggest magnetic fields in the infant universe might have altered nuclear reaction pathways, steering nucleosynthesis down unexpected routes. These ideas are thrilling, but they're also untested. Without direct evidence, they remain beautiful speculations. What makes this mystery so compelling is its stubborn persistence. The lithium problem has survived decades of sharper telescopes, better stellar models, and more precise nuclear data. Every proposed fix either falls short or demands radical revisions to well-tested physics. And that's the real lesson here. Sometimes the universe's quietest discrepancies, like a subtle shortage of one unassuming element, can point to the loudest gaps in our knowledge. Whether the answer lies in the stars, the lab, or the wild frontiers of cosmology, one thing's certain: lithium is more than just a metal. It's a cosmic Rosetta Stone waiting to be decoded. Imagine throwing a handful of sand into the wind and watching it scatter, not randomly but with a precise mathematical rhythm. That's the cosmic microwave background's fluctuations in a nutshell. Staggeringly close to what statisticians call Gaussian, meaning they follow a predictable bell curve pattern of randomness. On the surface, this might sound like a good thing, a sign of cosmic order. But here's the twist: some of our most promising theories about the universe's birth predict the CMB should be a little messy, a little non-Gaussian. The fact that it's not is like finding a perfectly smooth pond after expecting ripples. Beautiful but baffling. To understand why this matters, picture two types of static on an old radio. Gaussian static is pure noise, no hidden rhythms, no secret messages. Non-Gaussian static, though, that's where the whispers hide. Tiny deviations from Gaussianity in the CMB could reveal quantum jitters from the Big Bang, echoes of exotic particles, or even flaws in the fabric of spacetime itself. The Planck satellite, our sharpest eye on the CMB, spent years hunting for these subtle wrinkles. What it found was a sky so statistically pristine it left theorists scratching their heads. The deviations were there, but vanishingly small, like finding a single distorted grain in a desert of perfect sand. So why the mismatch? Inflation, the universe's hypothesized growth spurt, is the prime suspect. Most inflationary models suggest that as spacetime ballooned, quantum fluctuations got stretched into cosmic proportions. seeding the CMB's temperature variations. But many of these models also predict those fluctuations should carry faint non-Gaussian fingerprint subtle clustering or asymmetry in the hot and cold spots. The fact that we don't see strong signs of this forces a reckoning. Either inflation was simpler than we thought, or we're missing a crucial piece of the puzzle. One camp argues for single-field inflation, a minimalist version where just one quantum field drove the expansion, leaving behind near-perfect Gaussian noise. It's elegant, but maybe too simple, like explaining a symphony with a single note. Other theorists propose more exotic scenarios, like multiple fields interacting during inflation, which could have erased non-Gaussian traces like waves smoothing out footprints on a beach. Then there's the radical fringe, ideas like the universe being born from a collision of higher dimensional brains, which might leave entirely different statistical signatures we haven't even learned to read yet. The stakes here are cosmic. If the CMB's Gaussianity holds firm, it could mean that inflation, if it happened at all, was a far quieter, smoother process than we imagined. But if future telescopes like the upcoming Lightbird mission catch even a hint of non-Gaussian patterns, it could open a window into physics beyond our wildest theories. The universe's oldest light isn't just a relic, it's a cipher, and the key to decoding it might lie in the very thing we don't see. For now, the CMB's silence is its loudest mystery. Dark energy dominates the universe today, pushing galaxies apart at an ever-accelerating rate. But what if its fingerprints were there from the very beginning? The cosmic microwave background hints at a bizarre possibility. That dark energy didn't just switch on recently. It might have surged in the universe's first 100,000 years, left ghostly imprints in the CMB, then vanished for billions of years before roaring back. This phantom phase, dubbed early dark energy, is like finding a childhood diary entry predicting your exact midlife crisis, eerily precise and deeply confusing. The clues lie in how sound waves traveled through the infant cosmos. Picture the early universe as a scalding, dense plasma, rippling with pressure waves like an ocean in a storm. These waves left faint but measurable patterns in the CMB, and their spacing acts as a cosmic ruler, allowing us to measure the universe's expansion history with incredible precision. But when scientists compared these measurements to predictions from standard cosmology, something didn't add up. The waves seemed slightly offset, as if space had stretched faster than expected during those first critical epochs. Early dark energy could explain this bump in the cosmic timeline, a brief, extra push that tweaked the universe's expansion just enough to leave a mark. Now here's where it gets weirder. Today's dark energy is a slow, steady force, but early dark energy would have been a flash in the pan, a violent burst that flared up and faded almost instantly. Think of it like a car's turbocharger kicking in during the first few seconds of a race, then shutting off for the remaining 1,000 miles. This isn't just a tweak to the numbers, it challenges our understanding of what dark energy even is. Most theories treat it as a constant, the unchanging background hum of empty space. But if it can spike and vanish, then reappear billions of years later, we might be dealing with something far stranger, a cosmic chameleon that changes its behavior across time. Which brings us to the coincidence problem. Why does dark energy's rise to dominance happen to coincide with the era when humans evolved to observe it? The universe spent billions of years dominated by matter, with dark energy barely a whisper. Then, around 5 billion years ago, it suddenly took over. If early dark energy was real, it adds another layer to this mystery. Why would it activate twice, once at the dawn of time and again when galaxies had already formed? Some theorists suggest a link between these two phases, like a cosmic pendulum swinging between periods of acceleration. Others propose dark energy isn't a single force but a spectrum of phenomena with different manifestations across cosmic history. The implications are staggering. If early dark energy existed, it could solve other cosmological headaches like the Hubble tension, where different methods of measuring the universe's expansion rate disagree. A brief early kick might reconcile these conflicting results, but it also opens a Pandora's box of new questions. Was this an isolated event, or does dark energy pulse intermittently throughout cosmic history? Are we seeing the first hints of a universe that breathes in and out, alternating between stretching and stillness? For now, early dark energy remains a tantalizing but unproven idea. Future CMB experiments like the Simons Observatory will hunt for its subtle signatures with unprecedented precision. Whether they find them or not, one thing's clear: dark energy isn't just a modern phenomenon. It might be the universe's oldest trick, playing hide and seek across the eons, and every time we think we've pinned it down, it slips away, leaving behind only whispers in the afterglow of creation. One of the most stubborn disagreements in modern cosmology isn't about distant galaxies or theoretical particles. It's about a single number. The Hubble constant, the rate at which the universe is expanding, should be the same no matter how you measure it. But here's the catch: it isn't. When scientists calculate it using the cosmic microwave background, they get one value. When they measure it by tracking nearby supernova and stars, they get another. The difference might seem small, just a few kilometers per second per megaparsec, but in the precision-driven world of cosmology, it's a glaring rift. This is the Hubble tension, and it's shaking the foundations of how we understand the cosmos. Let's break it down. The CMB method relies on the afterglow of the Big Bang as a cosmic yardstick. By mapping the slight temperature fluctuations in this ancient light, scientists can reconstruct the universe's early expansion rate and extrapolate forward to today. It's like calculating how fast a train is moving by examining the spacing of its earliest track marks. But the local method takes a more direct approach, using pulsating stars called Cepheid variables and exploding supernova as mile markers. These act as standard candles, objects with known brightness, allowing astronomers to gauge distances and velocities in our cosmic neighborhood. It's the difference between predicting a train's speed from its starting engine power versus clocking it with a radar gun as it passes by. The problem: these two methods refuse to agree. The CMB, filtered through our best models of cosmic evolution, suggests an expansion rate around 67 kilometers per second per megaparsec. The local measurements, though, consistently land closer to 73. At first, researchers brushed this off as a calibration error or statistical fluke. But as observations grew sharper, the gap held firm. The odds of this mismatch being a coincidence, less than 1 in 100,000. Either we're missing something fundamental in our measurements, or the universe is playing by rules we haven't discovered yet. One tantalizing possibility is that dark energy, the mysterious force accelerating the universe's expansion, isn't constant. What if it's been subtly strengthening over time, throwing off our extrapolations from the early cosmos? Imagine a car gradually pressing harder on the gas pedal. The speedometer would read higher than you'd expect based on its initial acceleration. Alternatively, there might be unknown particles, like a new type of neutrino, adding extra energy density to the universe in its adolescence, tweaking the CMB's predictions. Some theorists even flirt with the idea of early dark energy, a transient phase of accelerated expansion in the universe's first few 100,000 years that left no trace except this lingering discrepancy. Then there's the elephant in the room. What if we've misjudged our local measurements, dust, peculiar motions of galaxies, or even subtle biases in how we select standard candles could be skewing the numbers? But after years of cross-checking, recalibrating instruments, and inventing new techniques like using gravitational waves as distance markers, the tension persists. It's as if the universe is handing us two conflicting blueprints, each impeccably drawn, yet impossible to reconcile. This isn't just academic quibbling. The Hubble constant is the backbone of cosmic distance calculations, the ruler by which we measure everything from the age of the universe to the fate of galaxies. If our ruler is broken, so are countless other predictions. The tension forces us to confront a humbling truth. Either our tools are flawed in ways we can't yet see, or the cosmos is hiding a secret more profound than we've dared to imagine. And that's what makes this mystery so electric. It's not just about numbers. It's about whether we truly understand the story the universe is telling us, or if we've been misreading its opening lines all along. Zoom in on the cosmic microwave background, past the familiar ripples and hotspots, and you might notice something downright eerie, faint, ghostly circles etched into the fabric of the universe. These aren't random artifacts or camera glitches. They're concentric rings like cosmic bullseyes scattered across the CMB with unsettling symmetry. The controversial claim, these circles could be bruises left by collisions with other universes before the Big Bang. Imagine dropping a pebble into a pond, watching the ripples spread. Except this pond is space-time itself, and the pebble is another universe bumping into ours. It's a dizzying idea, but is there any real evidence to back it up? First, the science behind the spectacle. If our universe is part of a multiverse, a vast foam of bubble universes endlessly inflating, then it's possible some of those bubbles once brushed against each other. The energy released in such a collision would ripple outward, imprinting perfectly circular patterns in the CMB's temperature fluctuations. Like cosmic sonar, these rings would encode information about the other universe's size, energy, and even the direction of impact. The most famous analysis, led by physicist Roger Penrose and colleagues, claimed to have found not just one or two of these rings, but dozens, layered like tree rings in the sky. But here's the catch: the scientific community remains deeply divided. Critics argue these circles could just be statistical noise, the kind of random fluctuations you'd expect in any complex dataset. Run enough simulations of a Gaussian sky, a universe with perfectly random temperature variations, and eventually you'll find patterns that look significant purely by chance. It's like searching for faces in clouds. Our brains are wired to see order in chaos. Independent teams analyzing the same data have struggled to reproduce Penrose's results, with some concluding the circles are no more remarkable than the occasional streak of luck in a game of cosmic dice. Yet the mystery refuses to fade entirely. Alternative explanations have emerged, like the idea of topological defects, knots in space-time formed during phase transitions in the early universe. These defects, called textures or monopoles, could theoretically decay in violent bursts, creating circular shockwaves in the CMB. Picture a soap bubble popping in slow motion, the collapsing walls sending out perfect rings of energy. If confirmed, these wouldn't require a multiverse to explain, but they'd still point to physics beyond the standard model. What makes this debate so electrifying is the stakes. If the circles are real, they're not just curiosities, they're portals to a realm before time, evidence of a cosmos vastly larger and stranger than we imagined. But if they're illusions, they're a cautionary tale about how easily we can fool ourselves into seeing order where none exists. Future CMB experiments with even sharper resolution may finally settle the argument. Until then, these phantom circles linger at the edge of discovery, daring us to decide: are we seeing the fingerprints of other worlds, or just the cosmic equivalent of static on a screen? In the wildest dreams of particle physics, there should be relics lurking in the cosmic microwave background, exotic, almost mythical particles called magnetic monopoles. Imagine a magnet sliced in half, but instead of getting a north and south pole, you're left with just one, a solitary north or south pole floating freely through space. That's a monopole, a particle that shouldn't exist under everyday electromagnetism. Yet grand unified theories, the bold frameworks aiming to stitch together all fundamental forces, practically demand their existence. These theories suggest that in the searing heat of the early universe, space-time itself could have sprouted defects like cracks in ice as it freezes, and these cracks would manifest as monopoles. The cosmic microwave background should be littered with their signatures, cosmic breadcrumbs from the universe's first fractions of a second. But here's the eerie part: we've searched and the CMB is utterly silent. It's as if someone erased every trace of these particles from history. Why does this absence rattle physicists so deeply? Picture grand unified theories as a majestic bridge connecting quantum mechanics and general relativity. A structure so elegant it promises to explain everything from the tiniest particles to the largest galaxies. Magnetic monopoles were supposed to be the bolts holding that bridge together, tangible proof that these forces were once one. Without them, the entire edifice wobbles. The simplest versions of these theories predict monopoles so abundant they'd outweigh all known matter in the universe. Clearly, that didn't happen, so where did they go? One escape hatch is cosmic inflation, the same rapid expansion that smooths out the CMB's temperature variations. If inflation kicked in right after monopoles formed, it could have stretched spacetime so violently that these particles were diluted to near nothingness, scattered so thinly that they're effectively invisible today. It's a neat fix, but it raises another headache. Inflation itself is still hypothetical, its trigger unknown. Relying on it to solve the monopole problem feels like using one mystery to patch another. Then there's the radical alternative: maybe monopoles never existed at all. Some theorists argue grand unified theories need serious tweaking. Perhaps the early universe found a loophole, a way to avoid producing these particles entirely. Others suggest monopoles are out there but hiding, clustered in regions of space we haven't probed yet, like cosmic needles in an unimaginably large haystack. The most daring idea: monopoles might not be particles in the traditional sense, but fleeting, unstable entities that decayed moments after birth, leaving only faint echoes in the quantum foam of spacetime. The silence of the CMB on this front isn't just a gap in our knowledge, it's a provocation. Every null result, every failed detection tightens the screws on our boldest theories, forcing them to evolve or crumble. Magnetic monopoles might still be waiting in the wings of the universe, but for now, their absence is louder than any signal, a cosmic riddle scribbled in the margins of the oldest light we can see. Neutrinos are the universe's quietest particles, nearly massless, barely interacting, slipping through planets like ghosts through walls. For decades, physicists assumed they weighed nothing at all. Then came the bombshell: neutrinos have mass, just so vanishingly small we still can't pin down exactly how much. The plot thickens when you compare two of our most powerful tools for weighing them: the cosmic microwave background and underground detectors like Katrin. The numbers should match. Instead, they're telling two different stories, and the gap between them could crack open our understanding of particle physics. Start with the CMB's approach. When the universe was a seething plasma of particles and light, neutrinos were like cosmic speedsters, zipping through space so fast they smoothed out the early universe's density fluctuations. The colder and slower they were, the more they'd clump. By measuring the CMB's delicate texture, how matter pooled into galaxies and voids, scientists can back-calculate the total mass of all neutrino species combined. The latest data from Planck and other observatories suggests an upper limit. Neutrinos couldn't have more than about 0.12 electron volts. That's billions of times lighter than an electron, so faint it's like trying to weigh a snowflake with a bathroom scale. Now shift to Earth. In a German lab buried under a mountain to block cosmic noise, the Katrin experiment takes a radically different tack. Instead of inferring mass from ancient light, it watches the decay of tritium, a radioactive isotope of hydrogen. When tritium decays, it spits out an electron and a neutrino, but because energy must be conserved, the electron's energy reveals the neutrino's mass. Katrin precision is staggering, capable of detecting shifts as tiny as 0.2 electron volts. Yet its latest findings hover just above the CMB's limit, hinting that neutrinos might be heavier than the cosmos allows. At first glance, the discrepancy seems small, fractions of an electron volt. But in physics, even a whisper of inconsistency can roar. If Catron results hold, it could mean one of three things. Our CMB models are missing a key ingredient, like an unknown particle darkening the early universe's dynamics. Or neutrinos might behave differently across cosmic time, their mass somehow evolving as the universe expanded. The wildest possibility, we're glimpsing signs of sterile neutrinos, a hypothetical fourth flavor of neutrino that interacts only via gravity, skewing both sets of measurements in ways we don't yet grasp. What makes this tension so electrifying is its reach. Neutrinos are everywhere. Trillions pass through your body every second, yet they're barely understood. If they're heavier than the CMB predicts, it could reshape everything from galaxy formation to the fate of the cosmos. Heavy neutrinos would slow the universe's expansion, alter how dark matter clumps, and even rewrite the timeline of the first stars. Conversely, if Catron results bend toward the CMB's limit, it might signal flaws in how we study tritium decay, forcing us back to the particle physics drawing board. For now, the neutrino remains a master of disguise, flickering between scales and slipping through the cracks of our best instruments. But every conflicting measurement, every stubborn decimal point is a clue. Whether the answer lies in the cosmos or the lab, one thing's certain: the universe's lightest particle is hiding some of its heaviest secrets. If you zoom into the cosmic microwave background, expecting to see a bustling metropolis of tiny temperature fluctuations, you might be in for a shock. On the largest scales, the CMB's ripples make sense: grand, sweeping variations that line up beautifully with our models of cosmic inflation and dark matter. But when you focus on the smallest patches of this ancient light, things get weirdly quiet. It's as if the universe's blueprint has all the right big strokes, but someone forgot to fill in the fine details. This unexpected smoothness isn't just a minor hiccup. It's a full-blown crisis for our leading theory of dark matter, shaking the foundations of how we think the cosmos assembled itself. Cold dark matter, or CDM, has been the gold standard for decades, an invisible, sluggish substance that clumps together under gravity, forming the scaffolding for galaxies. Simulations based on CDM predict a universe teeming with small-scale structure, like cosmic cobblestones littering the void. And yet, the CMB's small-scale fluctuations are suspiciously muted, as if vast swaths of the early universe were ironed flat. It's the equivalent of walking into a forest and finding no underbrush, no saplings, just towering trees with eerily empty spaces between them. One possible fix. Warm dark matter, unlike its sluggish cousin, WDM consists of lighter, faster-moving particles. Think neutrinos on steroids. These particles would zip through the early universe, smoothing out the tiniest density fluctuations like a cosmic rolling pin. The result: fewer dwarf galaxies, less small-scale clumping, and a CMB that matches those puzzlingly smooth patches. There's just one catch: if dark matter is warm, it might struggle to explain why we do see some small structures, like certain ultra-faint galaxies. It's a delicate balancing act: too much smoothing, and the theory wipes out structures we know exist; too little, and the CMB's silence remains unexplained. Then there's the action hypothesis, a dark horse candidate that's been gaining traction. Actions are hypothetical particles born from quantum field theory, absurdly light but abundant enough to collectively outweigh stars. Unlike WIMP or WDM, actions behave more like a wave than a particle, creating interference patterns that could naturally suppress small-scale clumping. Picture shaking a tray of sand. Most grains stay put, but a few ripple into delicate, large-scale patterns. If actions are real, they might have left exactly the kind of subtle, smoothed-over signature we're seeing in the CMB's finest details. To test these ideas, scientists run colossal simulations, digital universes where they tweak dark matter's properties, and watch how virtual CMBs evolve. One simulation might flood the cosmos with cold, slow-moving particles. Another might seed it with lightweight, speedy actions. The goal: to find a model where the simulated CMB's small-scale fluctuations disappear, matching the real thing. Some of these virtual experiments have come tantalizingly close, but none yet perfectly replicate the universe's quiet corners. What makes this mystery so profound is what it implies about dark matter's essence. Is it a single substance or a mix of different particles with conflicting behaviors? Does it interact with itself in ways we haven't dreamed of? Every unexplained pixel in the CMB's high-resolution map is a clue and a challenge. The universe's quietest patches might be whispering secrets about the nature of reality itself, if only we could learn to listen. For billions of years after the Big Bang, the universe was a fog, a thick soup of neutral hydrogen atoms soaking up every glimmer of light. Then something changed. Galaxies began flickering on like cosmic lighthouses, their ultraviolet radiation tearing electrons from those hydrogen atoms in a violent process called reionization. By the time the fog lifted, the universe had gone transparent, ready for starlight to travel freely across the cosmos. The cosmic microwave background holds a record of this pivotal transformation in its polarized light, a faint echo of that epochal shift. But here's the shock: reionization started late. According to our best models, it should have kicked off around redshift 15, when the universe was barely 300 million years old. Instead, the CMB's polarization patterns tell us the real timeline began closer to redshift 10, almost 100 million years behind schedule. It's as if the universe hit snooze on one of its most critical alarms. What caused this cosmic delay? The prime suspect is star formation specifically. The first generations of galaxies weren't pumping out enough ultraviolet radiation to ionize the hydrogen soup efficiently. Picture trying to boil a pot of water with a single candle. It's possible, but it'll take far longer than if you had a roaring flame. Early galaxies might have been smaller, dimmer, or more obscured by dust than we've assumed, their UV light struggling to escape and do its work. Some simulations suggest these pioneers formed stars at a trickle rather than a flood, their feeble output dragging out the reionization process. Others propose that vast reservoirs of cold gas in the early universe acted like sponges, soaking up UV photons before they could reach distant hydrogen atoms. The plot thickens when you consider the role of supermassive black holes. Today, quasars, the blazing cores of galaxies powered by voracious black holes, are ultraviolet powerhouses. But in the universe's first billion years, they were vanishingly rare. Without their intense radiation to assist, reionization would have relied entirely on puny stellar nurseries, stretching the timeline to match the CMB's stubborn data. It's a cosmic tug-of-war. Push reionization too early, and you overproduce UV light in models. Push it too late, and you contradict evidence from some of the most distant galaxies we've observed. Then there's the wild card, dark matter. If the earliest dark matter halos, the invisible scaffolds that held infant galaxies together, were somehow less efficient at funneling gas into stars, that could explain the sluggish start to reionization. Imagine a factory where the conveyor belts keep jamming. Even with raw materials available, the finished products roll out slower than expected. Some theorists speculate that interactions between dark matter particles could have subtly heated the primordial gas, making it harder for stars to form in the first place. Others wonder if magnetic fields in the early universe played an unexpected role, stifling star formation like an invisible hand pressing down on cosmic nurseries. The CMB's polarization maps offer tantalizing hints, but they're not the only clue. Deep field observations from the James Webb Space Telescope are now spotting galaxies from this elusive era, their faint light carrying fingerprints of the very first stars. Some show surprising bursts of star formation, while others appear eerily quiet, a patchwork of activity that might finally explain why reionization took its time. Every new dataset is a piece of the puzzle, and with each one we're closer to understanding why the universe waited so long to turn on the lights. One thing's certain: this isn't just about timing. The delay in reionization forces us to rethink how galaxies grow, how stars ignite, and how the cosmos transition from darkness to light. It's a reminder that even our grandest models are sketches, and the universe still holds surprises in its oldest shadows. The cosmic microwave background isn't just a static snapshot of the early universe, it's also a cosmic speedometer, revealing our galaxy's motion through space in stunning detail. When scientists first mapped the CMB's temperature variations, they noticed something peculiar. One half of the sky appears slightly warmer than the other, as if we're barreling through the afterglow of the Big Bang at over 600 kilometers per second. This so-called CMB dipole should, in theory, reflect the Milky Way's motion relative to this primordial radiation. But here's the catch: when you tally up all the gravitational tugs from nearby galaxy clusters and superclusters, they only account for about half that speed. It's like driving a car downhill and realizing gravity alone isn't enough to explain why you're accelerating. Something invisible is giving you an extra push. So what's behind this cosmic discrepancy? One possibility is that vast, unseen structures, colossal concentrations of mass beyond our observational horizon, are yanking us toward them. Imagine dangling a magnet near a pile of iron filings. Even if you can't see the magnet, the way the filings shift reveals its presence. Similarly, if there's a great attractor lurking in the cosmic shadows, a supercluster so massive it defies imagination, its gravity could explain our anomalous motion. Yet even the known great attractors, like the Shapley supercluster, fall short of accounting for the full dipole. That's where the dark flow hypothesis comes in, a controversial idea that our galaxy, along with thousands of others, is caught in a river of invisible momentum, all streaming toward something even farther away, perhaps a structure so distant its light hasn't reached us yet. The implications are staggering. If dark flow is real, it challenges the cosmological principle, the assumption that the universe is uniform on the largest scales. Instead, it suggests there are imbalances so vast they shape the motion of entire galaxy clusters across billions of light-years. Some theorists have even floated the idea that this flow could be the gravitational fingerprint of another universe beyond our own, a neighboring bubble in the multiverse brushing against ours. It's a dizzying thought, but here's the problem. We have no way to directly observe what's causing this pull. The suspected sources lie beyond the observable universe's edge, placing them forever out of reach. Then there's the skeptical take. Maybe we're misinterpreting the dipole altogether. Could it be not just a kinematic effect, our motion through space, but also a relic of primordial inhomogeneities, wrinkles in the CMB left over from the Big Bang itself? If so, that would mean the dipole isn't purely a speedometer. It's also a fossil, a whisper from the universe's first moments. Others argue that local effects, like the Milky Way's own rotation or the distribution of hot gas in our galactic neighborhood, might be skewing the measurements. But after decades of scrutiny, the anomaly persists, resisting every attempt to explain it away. What makes this mystery so electrifying is its sheer scale. The CMB dipole isn't just a quirk of data, it's a signpost pointing to forces that might redefine our understanding of the cosmos. Whether it's hidden mass, a flaw in our models, or something even more extraordinary, one thing's clear: the universe is still full of surprises, and the oldest light we can see is guiding us straight toward them. When we measure the cosmic microwave background spectrum, it matches a near-perfect blackbody curve, the kind of radiation you'd expect from an object in perfect thermal equilibrium. This precision is breathtaking but also baffling, because according to our models, the early universe should have been far messier, riddled with violent energy injections that ought to leave visible scars on this curve. Cosmic strings, hypothetical defects in space-time left over from the Big Bang, should have released bursts of radiation as they snapped. Primordial black holes, those ancient gravitational traps that might have formed in the universe's first seconds, should have evaporated in fiery explosions of Hawking radiation. Even something as simple as the heat from the first stars ought to have subtly warped the CMB's pristine spectrum. And yet, when we look, the blackbody curve is so flawless it's almost unnerving, like finding an untouched snowfield with no footprints in sight. Take cosmic strings first. These aren't your everyday threads. They're topological knots in spacetime itself, thinner than an atom but stretching across the cosmos, carrying unimaginable tension. If they existed, their vibrations would have sent out gravitational waves and electromagnetic shocks, dumping energy into the early universe's plasma. That energy would have heated pockets of the primordial soup, creating tiny bumps and wiggles in the CMB's spectrum called spectral distortions. The fact we don't see them suggests these strings either never existed, or if they did, their energy was so finely distributed that it blended seamlessly into the cosmic background. It's like dropping a handful of sand into the ocean and expecting to see ripples. Sometimes the universe is just too vast to notice the disturbance. Primordial black holes face a similar paradox. These aren't the black holes formed from collapsing stars. They're relics from the Big Bang's chaotic first moments, where dense regions of space might have collapsed under their own gravity. The smaller ones, those weighing less than a mountain, would have evaporated long ago, their final moments erupting in gamma-ray bursts that ought to have left imprints on the CMB's spectrum. Yet the data shows no sign of these fireworks. Either these black holes were far rarer than some theories predicted, or they evaporated in a way that somehow left no trace. Then there's the puzzle of late-time energy injections. When the first stars ignited, their ultraviolet light didn't just reionize the universe, it also heated the leftover electrons in the cosmic plasma. That heat should have subtly altered the CMB spectrum, creating distortions called Y-type and mu-type depending on when the energy was dumped in. The COBE and FIRA's satellites measured the CMB spectrum with such precision that they ruled out most of these distortions, placing tight limits on how much energy could have been injected and when. It's as if the universe had a thermostat keeping the temperature fluctuations within razor-thin margins. So what's the takeaway from all this silence? Either the early universe was surprisingly gentle, with fewer cosmic catastrophes than we imagined, or our models of these phenomena need serious revision. Perhaps cosmic strings decayed in ways we haven't accounted for, or primordial black holes clustered in regions that left the CMB untouched. Maybe the first stars formed later or burned cooler than our simulations suggest. Every missing distortion is a clue, a whisper from the past telling us that reality might be simpler or stranger than we thought, the most tantalizing possibility. That we're seeing hints of new physics. Some theories suggest exotic particles or unknown forces could have smoothed out these distortions, erasing them like a cosmic eraser. Others propose that the universe's expansion didn't just dilute matter and energy, it might have stretched out these spectral imprints until they vanished into the noise. Whatever the answer, the CMB's flawless spectrum isn't just a relic. It's a riddle, one that challenges us to look deeper into the shadows of cosmic history. The absence of distortions isn't an empty silence, it's a question, written in the oldest light there is. When astronomers peered into the cosmic microwave background's polarized light, they weren't just looking for confirmation of their theories, they were hunting for a ghost. Hidden in the subtle swirls of the CMB's polarization patterns are clues to the universe's most violent birth pangs, imprints of gravitational waves that may have rippled through space-time in the first trillionth of a second after the Big Bang. These aren't ordinary waves, they're echoes of cosmic inflation, the hypothetical moment when the universe expanded faster than light itself. And the key to finding them lies in something called B-mode polarization, a specific twisting pattern in the CMB's light that could either be the smoking gun for inflation or a cosmic mirage. Picture the early universe as a stormy ocean, with gravitational waves churning the fabric of space-time like underwater currents. As these waves pass through the primordial plasma, they left behind a distinctive fingerprint swirling patterns in the CMB's polarized light, much like the way wind creates spirals on the surface of a lake. These B modes are different from the more common E mode polarization, which comes from simpler density fluctuations in the early universe. B modes twist, curling in on themselves like the petals of a flower, and that twist is what makes them so tantalizing. If we could isolate them from other cosmic noise, they'd be direct evidence of inflation's gravitational waves, a window into energy's trillions of times higher than anything our particle colliders can reach. The hunt for these elusive signals reached a fever pitch in 2014 when the BICEP2 collaboration announced a bombshell discovery, B modes in the CMB that seemed to match predictions for primordial gravitational waves. Headlines declared it a Nobel Prize-worthy breakthrough, proof that inflation had indeed stretched quantum jitters into cosmic-scale ripples, but the celebration was short-lived. Further analysis revealed that much of the signal came from something far more mundane: interstellar dust in our own Milky Way, scattering light in ways that mimicked the telltale swirls. It was a cosmic case of mistaken identity, a humbling reminder that the universe loves to hide its secrets behind layers of deception. Today, the search has grown more sophisticated. Projects like the Keck Array and the South Pole Telescope have joined forces to map the CMB's polarization with unprecedented precision, separating the faint whisper of primordial B modes from the roar of galactic dust. The latest data suggests that if inflationary gravitational waves are out there, their signal is even weaker than we'd hoped, perhaps too faint for current instruments to detect. But that hasn't killed the dream. Upcoming missions like the Lightbird satellite are designed to scan the sky with even greater sensitivity, hunting for B modes across multiple frequencies to weed out dust's contaminating effects. The stakes couldn't be higher. If B modes from inflation are real, they'd confirm not just that the universe expanded exponentially in its first moments, but also reveal the energy scale at which it happened, clues to how gravity might unify with quantum mechanics. If they're absent, it could mean inflation was far gentler than our boldest theories suggest, or that we need entirely new ideas to explain the cosmos's startling uniformity. And then there's the wild card. What if the B modes we've glimpsed aren't from inflation or dust, but from something even stranger, like cosmic strings or phase transitions in the early universe's vacuum? For now, the CMB's polarization maps remain a tantalizing puzzle, a swirl of possibilities written in the oldest light we can see. Every new observation peels back another layer, bringing us closer to answering one of cosmology's biggest questions. Did the universe really begin with a bang, or was it something even more extraordinary? What if the cosmic microwave background isn't just a relic of the Big Bang, but a Rosetta Stone for a deeper layer of reality, quantum gravity? The long-sought marriage of general relativity and quantum mechanics has remained frustratingly out of reach, hidden behind energies so extreme they make particle colliders look like toys. But the CMB might be hiding whispers of this unified theory in its ancient light, etched into the fabric of space-time when the universe was smaller than an atom. Imagine zooming in on the afterglow of creation until the smooth canvas of the sky dissolves into a frothing ocean of space-time foam, where space and time themselves flicker in and out of existence like quantum bubbles. If this foam exists, its microscopic turbulence could have left faint scars on the CMB's polarization patterns, subtle swirls betraying the universe's granular structure at the smallest scales. Think of it like observing a pond's surface at two wildly different resolutions. On human scales, the water looks perfectly smooth, just as the CMB appears uniform to our telescopes. But zoom in close enough and you'd see chaotic molecular motion, the water's quantum dance. Similarly, if spacetime has a fundamental graininess, its quantum jitters during inflation might have imprinted fractal-like distortions on the CMB's large-scale patterns. Future observatories like the proposed CMB-S4 experiment could hunt for these anomalies, scanning the sky with such precision they detect deviations smaller than 1 part in a million. A single anomalous twist in the polarization could be the smoking gun for quantum gravity, a cosmic fingerprint left by the universe's smallest scales on its largest canvas. The parallels to LIGO's discovery of gravitational waves are striking. Before 2015, ripples in spacetime were purely theoretical until LIGO heard the chirp of 2 black holes colliding a billion light-years away. The CMB could offer an even more profound detection, not just waves in spacetime, but the quantum texture of spacetime itself. Where LIGO measures gravitational waves with laser beams bouncing between mirrors, CMB probes like LightBird would use primordial light as its ruler, searching for statistical anomalies in the polarization that no classical process could explain. It's the difference between listening for a symphony and analyzing the atomic vibrations of the violin's wood. One reveals the music, the other the instrument's deepest essence. Then there's the holographic principle, a radical idea suggesting our 3-dimensional universe might be a projection of information encoded on a 2-dimensional surface at its boundary. If true, the CMB could bear holographic noise, subtle correlations between distant points in the sky that mirror quantum entanglement's spooky action at a distance. Picture pressing a holographic sticker onto a balloon, then inflating it to cosmic proportions. The stretched-out image would still carry hidden links between seemingly unrelated regions. Some theorists argue that specific statistical asymmetries in the CMB's temperature fluctuations already hint at this phenomenon, like finding identical paragraphs in unrelated chapters of a book. Of course, the challenges are staggering. Quantum gravity signals, if they exist, would be buried under layers of cosmic interference, from galactic dust to the afterglow of the first stars. Teasing them out would require not just better telescopes, but new mathematical lenses to decode patterns we've never seen before. Yet the payoff could redefine physics. A confirmed quantum gravity imprint in the CMB wouldn't just validate string theory or loop quantum gravity. It would give us a time machine to the Planck epoch, the universe's first 10 to the minus 43 seconds, where the very concepts of space and time broke down. This isn't just about solving equations, it's about rewriting the origin story of everything. The CMB's quiet glow might be the only messenger brave enough to cross that primordial frontier, carrying secrets from a time before time. And if we learn to listen, it could whisper answers to questions we're only beginning to ask. The cosmic microwave background is often called a relic, a static snapshot of the universe's fiery infancy, unchanging across billions of years. But what if that's not entirely true? A handful of astronomers have dared to suggest the unthinkable, that the CMB might be flickering, not dramatically, not in ways that rewrite cosmology overnight, but subtly, in patches of sky that appear marginally warmer or cooler when observed decades apart. These claims, if verified, would send shockwaves through astrophysics, forcing us to reconsider everything from the nature of dark energy to the fundamental stability of spacetime itself. The evidence comes from painstaking comparisons of early CMB maps, like those from the COBE satellite in the 1990s, with modern observations by Planck and ACT. In these analyses, certain regions, some spanning hundreds of square degrees, appear to brighten or dim by fractions of a microkelvin over 20 years. It's the cosmic equivalent of watching a mountain range slowly breathe, its peaks and valleys shifting imperceptibly over generations. One team reported a curious hotspot near the constellation Taurus that seemed to intensify between 1990 and 2010. While another study flagged a swath of the southern sky cooling at a rate inconsistent with instrumental error. Skeptics, of course, have ready explanations. The CMB is buried under foreground noise, our own galaxy's dust, radio haze from distant quasars, even the solar system's motion through space. A 1% misestimation of these contaminating signals could easily mimic temperature variations where none exist. Then there's the challenge of calibrating instruments across generations. COBE sensors operated in a different technological era, with uncertainties that might not perfectly align with Planck's exquisitely sensitive bolometers. It's like comparing a charcoal sketch to a high-resolution digital photo and wondering why the shading doesn't match. Even the universe's expansion plays tricks. As light from the CMB redshifts over time, its spectrum technically cools, but this effect is uniform and predictable, not the patchy flickering being claimed. But let's entertain the wild scenario where these variations are real. What could possibly cause a 14-billion-year-old fossil radiation to twitch? One provocative idea involves late-time dark energy interactions. If dark energy isn't a constant but a dynamic field, its fluctuations might subtly alter how CMB photons lose energy as they traverse expanding space. Think of it as a cosmic dimmer switch, slightly adjusting the brightness in certain rooms of the universe. Alternatively, vast cosmic structures, superclusters or voids, could be acting as gravitational lenses on a grand scale. As these titanic masses shift over epochs, their warping of spacetime might magnify or dim background CMB light in ways that mimic temperature changes. The boldest hypothesis that we're seeing evidence of a multiverse. In some string theory models, collisions between neighboring universes could transfer energy across dimensional boundaries, leaving transient scars in the CMB that fade over centuries. It's an intoxicating idea, but here's the rub. Proving it would require ruling out every mundane alternative, from instrument drift to galactic weather. Future experiments might settle the debate. The proposed CMBHE project aims to map the sky with 100-fold better resolution, while space-based interferometers could monitor specific patches continuously for decades, creating a time-lapse movie of the CMB's faintest whispers. For now, these flickering claims remain on the fringe, intriguing anomalies rather than paradigm shifts. But that's the beauty of the cosmic microwave background. Even after 60 years of study, it still holds mysteries that refuse to fit neatly into textbooks. Whether these variations are cosmic ghosts or mere measurement quirks, they remind us that the universe's oldest light still has stories left to tell, and some of them might be happening right now. Among the most dramatic relics predicted by grand unified theories are cosmic strings and textures, defects in spacetime itself, formed when the fundamental forces of nature froze into their current state during the universe's infancy. Picture the early cosmos as a seething ocean cooling into ice. Just as cracks form when water solidifies, the fabric of reality should have fractured into bizarre one-dimensional strings and tangled topological knots. These defects wouldn't just sit idly. Cosmic strings, thinner than a proton but stretching across the universe, would vibrate like guitar strings, emitting gravitational waves. Textures, more complex regions where spacetime folds in on itself, would collapse in violent bursts of energy. Both should have left glaring scars in the cosmic microwave background, sharp, linear temperature spikes for strings and bullseye-like hot and cold spots for textures. Yet when we scan the CMB with our most powerful telescopes, those scars are nowhere to be found. The sky is suspiciously smooth, like a pane of glass with no cracks. To appreciate how strange this absence is, consider what the CMB should look like if these defects existed. Simulations of cosmic strings predict distinctive step-like discontinuities in the CMB's temperature, sudden jumps where the string's gravitational pull warps the path of photons. Imagine dragging a knife through a painting. The edges of the cut would show abrupt shifts in color. Similarly, textures would imprint concentric rings of hotter and colder plasma, resembling ripples from a stone tossed into a pond. Side by side, the actual CMB maps and the defect-laden simulations couldn't look more different. One is a tapestry of gentle, Gaussian fluctuations. The other looks like it's been slashed and stitched back together by a cosmic tailor. So where did all the defects go? One possibility is that the phase transitions in the early universe, the moments when forces like electromagnetism and the weak nuclear force split apart, were far smoother than grand unified theories suggest. If the transitions happened gradually rather than abruptly, space-time might have avoided cracking altogether, like cooling glass slowly to prevent shattering. Alternatively, inflation, the universe's exponential expansion, could have stretched these defects so thin they effectively vanished, diluting their signatures beyond detection. It's like zooming out on a cracked windshield until the fractures blur into invisibility. But the plot thickens when you consider hybrid scenarios. Some models propose that defects did form, but only briefly, like ice forming on a lake only to melt moments later. In these transient defect theories, the universe's violent early energy fluctuations caused strings and textures to decay almost instantly, their energy dissipating before they could leave lasting imprints. Others suggest defects might still exist, but in regions of space so distant their light hasn't reached us yet, or in dimensions beyond our perception. The most radical interpretation, that grand unified theories themselves need revising. If the cosmos refuses to cooperate with our predictions, perhaps we've misunderstood how symmetry breaks on fundamental scales. Some theorists are exploring alternatives where defects form differently, not as strings or textures, but as more subtle, diffuse structures that blend into the CMB's noise. Others argue defects might interact with dark matter in ways that erase their usual signatures. What makes this absence so electrifying is what it reveals about our cosmic blind spots. The missing defects aren't just failed predictions, they're signposts pointing to gaps in our understanding of how the universe stitches itself together. Every smooth patch of the CMB is a silent challenge, a dare to dig deeper into the quantum forge where space, time, and forces were born. Whether the answer lies in gentler physics, hidden dimensions, or something entirely unimagined, one thing's certain: the universe's quiet perfection is louder than any defect could ever be. Hidden in the cosmic microwave background's delicate temperature fluctuations lies a ghostly whisper, a signal that the universe might contain more stuff than we can see, touch, or even detect with our finest instruments. This enigma revolves around a number called Neph, the effective number of relativistic species in the early cosmos. According to the standard model of particle physics, the early universe should have been filled with just 3 types of lightweight, fast-moving particles: the known neutrinos, electron, muon, and tau varieties zipping through space at near light speed. But the CMB tells a different story. Its precise measurements suggest Neph hovers around 3.4, a tiny but stubborn excess that defies expectations. It's as if the universe's ledger has an extra line item, an invisible contributor to the cosmic energy budget that no one can account for. Enter dark radiation, an umbrella term for any mysterious, lightweight particle that could have flooded the early universe, leaving only subtle gravitational fingerprints in the CMB. Imagine standing in a pitch-black room, sensing the air shift as someone silently walks past you. Dark radiation is like that unseen presence. It doesn't absorb or emit light, but its gravitational influence nudges the CMB's patterns in detectable ways. The leading candidate, sterile neutrinos, hypothetical cousins to the 3 known neutrinos, but with a bizarre twist, they interact only through gravity, making them virtually undetectable except through their cosmic side effects. If they exist, sterile neutrinos could have been born in the Big Bang's frenzy, then drifted through the expanding universe like spectral hitchhikers, subtly altering how matter clumped together in ways the CMB preserves. But sterile neutrinos aren't the only players in this shadowy drama. Some theories propose entire hidden sectors of particles, entire families lurking beyond our detection, connected to our world only by the faintest gravitational tugs. Picture a grand ballroom where the known particles, quarks, electrons, photons, dance under a glittering chandelier. Dark radiation would be the guests in an adjacent, invisible hall, their music just audible through the walls, their presence felt only by the way they warped the floorboards beneath everyone's feet. These hidden particles could include actions, gravitinos, or even exotic entities from higher dimensions, as predicted by string theory. Each would leave a distinct imprint on Neph, like different instruments tuning the CMB's symphony. The stakes here are cosmic. If dark radiation is real, it could solve multiple puzzles at once. For one, it might explain why the universe's expansion rate, the Hubble constant measured from the CMB, clashes with local observations. Extra-relativistic particles in the early universe would have tweaked the expansion history, reconciling the mismatch. It could also shed light on dark matter's nature. Some sterile neutrinos, for instance, might have slowed down just enough to become the elusive dark matter we hunt today. And then there's the grandest possibility of all. That dark radiation is a messenger from extra dimensions, a sign that our universe is but one layer in a vast, multidimensional reality. Yet for all its promise, dark radiation remains a specter. Efforts to pin it down in labs have come up empty. Experiments like the mini Buoni neutrino detector have glimpsed anomalies that could hint at sterile neutrinos, but the results are hotly debated. Meanwhile, the CMB's signal, while tantalizing, sits right on the edge of statistical significance, a whisper too faint to confirm, too persistent to ignore. Future observatories like the Simons Observatory or the proposed CMB S4 aim to measure Neph with precision sharp enough to settle the debate. Either they'll catch dark radiation red-handed, or they'll force us back to the drawing board, wondering what else could have left this ghostly signature in the universe's oldest light. What makes this mystery so thrilling is its sheer audacity. We're not just mapping the cosmos, we're eavesdropping on its hidden corners, listening for particles that might not even belong to our reality. Whether the answer lies in sterile neutrinos, hidden dimensions, or something stranger still, one thing's clear: the CMB isn't just a relic of the past. It's a treasure map pointing us toward the universe's best-kept secrets. The cosmic microwave background shouldn't care about galaxies. It's the oldest light in the universe, a relic from a time before stars, before planets, before matter had even clumped into recognizable structures. Yet when astronomers compare the CMB's temperature map to the distribution of modern galaxy superclusters, something bizarre emerges. Hot spots in the ancient afterglow seem to whisper to clusters of galaxies billions of years later, as if the universe's birth certificate had secret instructions for where cities would one day rise. It's like finding a child's fingerprints mysteriously engraved on a sculpture they wouldn't carve until adulthood, a cosmic paradox that's either a staggering coincidence or a clue to physics we've yet to grasp. Take the so-called axis of evil, the controversial alignment where CMB hotspots eerily trace the plane of our solar system. Skeptics dismiss it as a fluke, a quirk of statistics amplified by human pattern-seeking brains. But the plot thickens when you zoom out. Certain superclusters, colossal filaments of galaxies like the Sloan Great Wall, appear to stretch toward these same hotspots as though drawn by invisible threads. Simulate a universe without this connection, and the odds of such alignments happening by chance drop to less than 1 in 1,000. It's as if the universe's largest structures are subtly bowing to something imprinted in its oldest light. Enter backreaction, a radical idea that turns conventional cosmology on its head. Normally, we assume the CMB's patterns were frozen in place during inflation, then passively observed as matter later assembled into galaxies. But backreaction suggests the opposite, that colossal superclusters with their immense gravitational pull might have warped the CMB retroactively. Picture throwing a rock into a pond, then watching the ripples flow backward to distort the moment the water was poured. In this unorthodox view, the gravitational wells of modern galaxy clusters could have bent the paths of CMB photons over billions of years, imprinting their locations onto the primordial sky. Einstein's general relativity technically allows for such effects, but the math is fiendishly complex, and most models dismiss them as negligible. Yet if the alignments are real, they'd force us to rewrite cosmic history with gravity's echoes flowing both forward and backward in time. Then there's the integrated Sachs-Wolf effect, a proven but subtle phenomenon where CMB photons gain or lose energy as they traverse growing cosmic structures. Superclusters acting as gravitational hills and valleys should leave faint imprints on the CMB's temperature, but the observed correlations appear stronger than predicted. Some theorists speculate this could hint at dark energy's fingerprints, its repulsive force accelerating the expansion of space in ways that amplify these overlaps. Others propose more exotic explanations, like primordial magnetic fields twisting the cosmos's architecture into unexpected shapes, or even quantum entanglement spanning eons, linking the birth of spacetime to its mature structures. Visualizing this connection is like watching a cosmic ballet where the dancers are separated by billions of years. Fly-through simulations reveal superclusters' luminous webs of galaxies threading along invisible lines radiating from CMB hotspots, their motions eerily synchronized. It's as if the universe's first moments contained a hidden blueprint, a gravitational melody that galaxies are still humming to. Whether this harmony is a mirage or a masterpiece, one thing's certain: the CMB isn't just a snapshot of the past. It's a living puzzle, its pieces still shifting in the dark. Picture this: a distant future, trillions of years from now, when the cosmic microwave background, the very echo of creation, has faded to near nothingness. What we see today as a faint glow bathing the entire universe will have dimmed into oblivion, stretched into radio waves so long and weak they'll dissolve into the silence of space. The afterglow of the Big Bang, our most direct window into the universe's birth, is slowly but surely vanishing, and with it the most crucial evidence of how everything began. This fading isn't just a matter of light growing dimmer. As the universe expands, space itself stretches the CMB's photons, shifting them from microwaves to longer and longer wavelengths. Eventually, they'll be stretched so thin they'll lose all detectable energy, like a whisper drowned out by the wind. Compare this to the redshift of distant galaxies, another key piece of evidence for cosmic expansion. While galaxies will continue to recede and redshift, their light will also grow fainter over time, but they'll still leave behind a trace, a ghostly fingerprint of motion. The CMB, however, won't just fade, it will effectively disappear from the observational record, erasing the most universal signature of the Big Bang. For civilizations evolving in this far future cosmos, the universe will tell a very different story than the one we know. Without the CMB, they'll lack the most definitive proof that the cosmos began in a hot, dense state. Imagine trying to reconstruct Earth's history without fossils, without any remnants of dinosaurs, ancient plants, or early humans. Future astronomers might look out into a night sky dominated by aging stars and galaxies drifting ever farther apart, with no obvious clue that everything was once compressed into a single point of infinite energy. They could still infer expansion from galactic redshifts, but without the CMB's uniform glow as a reference, they might never grasp the full scale of cosmic history. This raises a haunting question: are we living in a privileged era, one of the only times in the universe's lifespan when the CMB is still detectable? If intelligent life arises too late, they might never know the universe had a beginning at all. They could mistake the darkness between galaxies for an eternal, static void, never suspecting the explosive origins now so obvious to us. The concept of a Big Bang might become as speculative to them as the multiverse is to us, an idea without concrete proof, debated by theorists but impossible to confirm. Yet, even as the CMB fades, other cosmic clues might endure. The distribution of elements like hydrogen and helium, forged in the first few minutes of the universe, will persist in stars and gas clouds. The large-scale structure of galaxies, the vast web of clusters and voids, might still hint at an ancient, rapid expansion, but these traces are indirect, open to interpretation. Without the CMB's unambiguous signal, the story of creation could become fragmented, lost to time like an ancient language with no surviving dictionary. This slow erasure of cosmic memory forces us to confront a profound truth. The universe isn't just changing, it's actively forgetting. The very evidence that unlocked its origins for us will one day vanish, leaving future generations with a puzzle missing its most crucial pieces. It's a humbling reminder that knowledge isn't eternal. There are windows in time when certain truths are visible and others when they are lost forever. For now, we're lucky enough to live in an era where the echoes of the Big Bang are still loud enough to hear. But in the unfathomable depths of the future, the universe's first light will finally go dark, taking its secrets with it. What we've uncovered in the cosmic microwave background isn't just a collection of anomalies, it's a trail of cosmic breadcrumbs, each one leading us closer to truths that could rewrite physics itself. From the eerie alignment of the axis of evil to the ghostly whispers of dark radiation, these 25 mysteries aren't mere curiosities. They're signposts pointing toward gaps in our understanding, cracks in the foundation of cosmology where something far stranger might be lurking. The CMB is more than a relic of the past. It's a living riddle, a puzzle that evolves with every new discovery, challenging us to look deeper, think bolder, and question everything we think we know. Think of it this way: every time we've peeled back a layer of the universe's mysteries, we've found not answers but grander questions waiting beneath. The CMB is no different. Its flawless blackbody spectrum, its puzzling hemispherical asymmetry, its missing large-scale fluctuations, these aren't flaws in the data. They're invitations to reconsider the nature of dark matter, to question whether inflation truly happened, even to wonder if our universe is just one bubble in an unimaginably vast multiverse. These breadcrumbs are scattered across 14 billion years of cosmic history, and we've only just begun to follow them. But here's the beauty of it: you don't need a telescope to join the hunt. Every one of these mysteries is a story still being written, and every new observation, every fresh pair of eyes, could be the key to unlocking the next chapter. That's why the CMB isn't just for scientists. It's for anyone who's ever looked up at the night sky and wondered how it all began or where it's all headed. These cosmic whispers belong to all of us, so let's keep asking questions. Let's stay curious, stay skeptical, and above all, stay hungry for the next revelation. Because the universe isn't done surprising us yet, and who knows, the next great cosmic breakthrough might start with you. Which of these 25 mysteries fascinates you the most? Drop your thoughts in the comments below. We want to hear which cosmic riddle keeps you up at night. And if you're craving more deep dives into the wonders of space, don't forget to hit subscribe. The universe has plenty more secrets to share, and we're just getting started.